Hello and welcome to another Math 104 lecture. Today what we're going to be looking at is we're going to be continuing functions. So we're going to be continuing in the chapter 2.4, again, if you're following along with the textbook. This is where we're going to be discussing function operations, and we'll also be skipping a couple sections. So most of what we'll be covering today is going to be found in chapter 2.8. So once again, if you're following in the textbook, 2.8 is where you're going to find the most of what we're looking at today. So last time we left off, we finished talking about increasing and decreasing, and we were talking about graphs of functions, how to tell when something is increasing or decreasing, and telling the domain and range of a function just by looking at the graph. Today what we're going to do is we're going to be looking at function operations. So we're going to get back more to the actual operations part of mathematics, like adding, subtracting, all that good stuff, but how exactly we do it with functions. So there's four main properties of operations for functions, just like there are for any real number. So the four properties are, as you could probably guess, addition, subtraction, multiplication, and division. So assume that f of x, I'm going to write out the four properties here. Assume that both f of x and g of x, both of them are functions of the variable x. Assume that they are non-zero functions, which means that f of x is not equal to 0 and g of x is also not equal to 0. Okay, so for addition, we have the following. We have f plus g of our variable x. Well, what this tells us is this is really our function in regards to x plus our other function in regards, also in regards to x. So function f and function g. So if you see this notation where you see f plus g and it says that, okay, you're adding the functions together, what does that really mean? Well, that's telling you, okay, you can split up the functions and just, replace them with whatever the functions are defined by, however the equation was originally defined, and just add them together. And similarly, you're going to see the same thing for subtraction. So if you have f minus g in regards to x, well, that's the same thing as if you had f of x minus g of x. Thirdly, you're going to have multiplication here. So that's if you have f times g in regards to x, that is the same thing as if you once again split things up. So if you had your first function multiplied by your second function. And last but not least, division, and I should probably number these. So 1, 2, 3, and 4. So for division, this is where you have f divided by g, and this is why we said assume that f and g are non-zero functions, because if g were a zero function, you'd be dividing by 0 here, and that wouldn't be okay. But assume we're dividing our two functions, f divided by g, still in regards to x. Well, then this is the same thing as if you split things up and you had your function of f on top and your function g on bottom of the fraction. Okay, so this all really shouldn't seem too out of the ordinary, but it'll probably solidify here when we do an example together. Okay, so what we're going to do is we're going to do addition and subtraction together, and then I'll bring you guys in for your classwork assignment. So let's go ahead and let's let f of x equal to 3x minus 1 and g of x equal x squared plus 2. What I want to do is I want to find, so over here, find f plus g of x and f minus g of x. Okay, so we're going to find these two together. Let's go ahead and work through these. Okay, so working through the addition one, f plus g in regards to our variable x. Well, like I said, way back up here for our rule, it's as if you split them up into the two different functions and then add the two different functions together. Okay, so that just says, okay, well, if we have f of x being 3x minus 1 and g of x being x squared plus 2, this is as if we're taking 3x minus 1 and adding it to x squared plus 2. And now all you have to do is just combine like terms, right? We can drop those parentheses off. So dropping the parentheses, we just have 3x minus 1 plus x squared plus 2. And we add like terms. And the only things that we can add are the constants because there's nothing that we can add to x squared. There's no other term that's in regards to x. So we just have x squared plus 3x. And now we can add the constants here. So -1 plus 2 gives us a +1. And now we have solved for f plus g of x. And it's that simple. All you're doing is you're just taking your two different functions and adding them together. So similarly, if we're going to do the subtraction one next, so that's f minus g of x, well, you write this in the order that it's presented. So because f is first, that means you're going to write your function f first. So that means we're still going to have 3x minus 1 out front. This time we're going to have a minus sign, and now we're going to have the x squared plus 2. Now the difference here is that because we're subtracting, you're going to take this negative sign and distribute it to both of the pieces here, right? So as a result, we can drop the first parentheses and it'll be 3x minus 1, but now it'll be minus x squared minus 2 instead of the addition of both of those. And once again, we try to condense like terms, and I'm always particular to putting my highest power out front, even though it's negative. So I'm going to put my negative x squared out front. I'm going to have my plus 3x because once again, there's nothing that's going to condense with our 3x. And now we have a -1 minus 2 as opposed to plus 2. So -1 minus 2 gives me a -3, and we're done here. Okay, so we've seen here f minus g of x, all you're doing is you're taking f of x, which is defined by 3x minus 1, and g of x, which is defined by x squared plus 2, and you're taking the g of x and subtracting it from f of x. And that's all it is. Okay, so go ahead, give your shot at the first classwork assignment. And the first classwork assignment, once again, is f times g in regards to x. So that is, and I'll write it here, f times g of x. So try it, see what you come up with, and we'll go through it together in just a second. Okay, so going through it together, let's figure this one out. Once again, what this tells us is we're going to take our two different functions. We're going to have f of x and g of x, and we're going to multiply them together. So this is going to say we're going to have the 3x minus 1. Sorry, that did not come out clear. Minus 1. There we go. 3x minus 1. And over here, we're going to have x squared plus 2. And now you realize, oh, yeah, this is just a binomial times a binomial. Binomial, once again, just means that it's two terms in each of these parentheses, right? So as a result, we can just FOIL these. So foiling, well, FOIL means first, outside, inside, last, right? That's how you distribute when you're multiplying two terms against two terms. So doing the first term, I'm going to write these all in different colors. So first term is positive 3x times positive x squared. So that's going to give us 3x cubed. Okay, so that was first. Now we do outside. So outside is 3x and the positive 2. So that's going to give us plus 6x, right? You're just multiplying the 2 times the coefficient of x, so 2 times 3x is 6x. Now we do inside, so that's going to be the -1 and the x squared. So -1 times x squared, you're just flipping the sign, right? So now you're just going to make it negative x squared. And last but not least, you have last, which is -1 times positive 2, which once again flips the sign and makes it -2. And there's really not much else that you can do other than put it in descending order of powers. So I'm just going to have my highest powers going first. So 3x cubed minus x squared plus 6x minus 2. And that's as far as you can take this, right? All this really is just practice from, going way back to, when we were talking about expanding polynomials or multiplying polynomials. In reality, that's all this question was, right? You were just taking your two functions, which were just two binomials, multiplying them together, and you got the following. Okay, so we got 3x cubed minus x squared plus 6x minus 2, and that's it, and we're done. Okay. For the sake of argument, I know I'm not doing an example of f divided by g. We haven't gotten to polynomial division yet. However, there's some cases which I do just want to point out. There are some cases that you can absolutely solve just either by factoring or by using keep change flip method. And those are the questions, or those are the types of questions that you will see on your homework. Okay, so when you see f divided by g of x, even though there's no example here, just use what you already know, and I promise that that'll be enough to get through the homework. Okay. All right, so let's go ahead and clear all this off here, and let's move on. So now what we're going to look at, since we just talked about, the different operations that we can do with functions, let's talk about the domain of combined functions. So the domain of a combined function is essentially when we're taking two functions, and like adding them together, subtracting them, doing some operation like we just had above. But what we need to do is trying to find the domain of that can be a little bit tricky. So let's look at another example here. Let's let f of x equal square root of x minus 1. Okay, and let's also let g of x equal square root of 3 minus x. Now, before we continue, before I even say, what we're trying to find the domain of, red flags should be going off in your head, right? I'm saying that we're supposed to be talking about domain here, which means that we're going to be trying to find some interval, right? And there's two important rules that we keep bringing up every time we talk about domain. One of them is that your denominator cannot be 0, right? So if you have a variable in the denominator of a fraction, you have to find where that could be 0 because you have to exclude that point. And the second thing, which is, again, this is why the red flag should be coming up in your head, is because when you have an even-powered root, you cannot have a negative underneath that even power. So we see that in both of our functions, we have a square root. So we're going to be looking to find where this, where these equations or where these functions would be negative. Okay. So what I want to do is I want to find the domain. So find the domain of f plus g of x. So we notice here that this is now going to be a combined function, right? We're taking two functions, we're adding them together, and we're trying to find the domain of the new function. We're trying to find the domain of f plus g of x. So what you have to do to solve this is you have to find the domain of each function individually. So that means finding the domain first of f of x, and also finding the domain of g of x. Once you do that, you rule out the points that are not in common. So we're going to look and we're going to see, obviously, these are different functions, so these are going to have different domains. Once you find the different domains, the true domain, the domain of this combined function here, the f plus g of x, is going to be wherever the two original domains agree. So it's going to be wherever the domain of f of x agrees with the domain of g of x. It's where the domains share points in common. Okay, so let's go ahead and do one at a time here, and it'll make more sense when we figure this out. Okay, so let's first find the domain of f of x. So domain of f of x. Okay, so finding the domain of f of x, once again, we see here that f of x is the square root of x minus 1. Once again, like we just talked about, the only stipulation that we have is it can't be negative, right? It can be positive and it can be 0, right? Square root of 0 is still 0, and that's totally okay. So all we can't have here is a negative number. So what we do is we set the radicand, which is, everything that's underneath the radical sign, to be greater than or equal to 0. Okay? And now all we have to do is just solve for a variable, right? And this is really easy. We just add 1 to both sides to isolate for our variable. So we get x is greater than or equal to 1. And what does this tell us as far as interval is concerned? Well, this is telling us that we are starting from 1 and we're including 1, right? Because it's greater than or equal. So we're starting from 1 and we're talking about all the numbers that are larger than 1. And that's what comprises the domain of f of x. So our interval notation for f of x is from 1 to infinity. And once again, this should make sense because if we go back up here to f of x, if we plug in any number that's bigger than 1, say 3, for example, you get the square root of 3 minus 1, which is the square root of 2, and that's a real number. Yeah, it's a decimal. We don't necessarily know what it is. It's like 1.14 or something. It goes on and on and on. It's an irrational number. But point is that it is a real number. However, if you pick any number that is less than 1, so if you pick any number such as 0, well, you would get 0 minus 1 underneath the radical sign, and then you have the square root of -1, and that's a problem, right? You have a negative number underneath the square root, and that's not okay. So now we found the domain of f of x. Let's now find the domain of g of x. So I'm just going to put quotation marks, domain of g of x. And we do the exact same thing, right? The only stipulation here is that it can't be a negative. So we set 3 minus x to be greater than or equal to 0. So 3 minus x greater than or equal to 0. Well, I'm going to add both sides by x, and you can do this in two different ways. You can either try to isolate x, or you can recognize that x is negative, so adding both sides by x would actually move x over to the other side, and it'll now be positive. That's probably the easiest way. So adding x to both sides, you now have 3 is greater than or equal to x, and if you don't really see what this means, you can just flip it to be the other way, which is x is less than or equal to 3. And what does this tell you? Well, once again, this is telling you that we're taking all the negative numbers, all the possible negative numbers, such as, starting from negative infinity all the way up until we hit 0. 0 is okay because it's still less than 3. And then 1, 2, and including 3 are also okay, right? We have a hard stop at 3. So our interval is from negative infinity to 3, including 3. And once again, we can test this idea, right? If we pick 4, for example, well, if we put 4 into g of x, we would have 3 minus 4 underneath the radical sign, which gives you -1. And notice, again, we get a negative number. It's outside of our domain. However, if you pick any other negative number, right? If you pick something that's going towards negative infinity, a great example, let's just do -17, for example. If you have now -17 for x, in g of x, you would have 3 minus a -17. And remember, two negatives cancel out, so you would really have 3 plus 17, and you have the square root of 20, which is a positive number, which means that this is totally okay. So all negative numbers are going to work, and all of the positive numbers up until you hit 3 are all going to work, including the number 3. So fantastic. We have now solved for our two domains. We have a domain that goes from negative infinity to 3, and we also have another domain that is from 1 to infinity. And our job here is we have to figure out the domain of f plus g of x. So remember, our goal here is still this piece right here. And the way that we figure out the domain of that is seeing and identifying the points at which these two domains agree. So this one right here and this one right here. And if you can't see it immediately, put it on a number line, okay? So what I suggest doing is make one number line, if possible, if you have two different colors, two different markers or pens at home, whatever the case may be. Try, doing this so that way it makes a little more sense here. So for the first one, we see that we're starting from 1. So we're going to start from 1, and I'm going to write this in blue for this guy here, for f of x, for the domain of f of x. I'm going to write this in blue. So we're starting from 1, and we're going all the way to infinity, right? It's going on towards positive infinity. And now for this one down here, I'm going to do this one in red. So in red, we're talking about all of the negative numbers up until it hits 3, right? So I just want to write 3 over here. So I have 3. And we're talking about all the negative numbers that go all the way up until we hit 3. And we stop right here, right? And the last important thing that you have to do is whether or not you're including those endpoints, right? Are you including 1? Are you including 3? And when you look at the intervals that we decided on, we realize, yes, we're including 1, yes, we're including 3. So I'm going to put dots for both of them, filled in dots. We are including that point. We are including that point. So yes. So now all you have left to do is just say, okay, well, where does this agree? Where is the part that both of the domains work? And turns out it's going to be this piece right here where both of the domains work out. And because both of your endpoints are, included here, your final domain for the domain of f plus g of x is from 1 to 3, including those endpoints. So you're talking about all of the numbers between 1 and 3. And remember, we're not just talking about integers, right? So don't be fooled. We're not just talking about 1, 2, and 3. There's also 1.25, 1.5, so on and so forth. There's infinitely many numbers between 1 and 3. They just happen to be, fractions. Okay, so all of the numbers between 1 and 3, including 1 and 3, are in the domain for this function here, f plus g of x. And if you're wondering what f plus g of x actually looks like, well, again, just to give yourself more practice, all this is taking your two functions and adding them together, right? So f plus g of x is really just f of x, which is x minus square root of x minus 1, plus g of x, which is the square root of 3 minus x. And you really can't simplify this anymore. This is as best as you can really do. You could do some manipulation to kind of get it a little better, but it's going to look really ugly. So point is that you're best off leaving it like this. And the domain of this entire piece here is what we just figured out, which is from 1 to 3, including the endpoints. Okay, so once again, just want to hammer down your procedure here. Your idea for when you're dealing with combined functions, keyword is combined because we're going to be looking at another term here, which is composition of functions. But when you're dealing with combined functions, which is when you have two functions and an operation that ties them together, be it addition, subtraction, multiplication, division, you're always going to be taking the domain of each original individual function and then seeing where they agree. So we take the domain of f of x, we take the domain of g of x, and then we see where they agree together. And that's how it works out. Okay, so why don't we go ahead and move on? And what we're going to talk about now is we're going to discuss composition of functions. So once again, what we just talked about is combined functions. This is now composition of functions. So let's go ahead and assume that, assume f and g are both functions of x, okay? So our functions, I'm just abbreviating functions of x. Then f composed with g, I see my handwriting is deteriorating as I go on, so f composed with g of x is equal to f of g of x. Now I wrote that in plain English, okay? And the way that we write this as a composition is you would write f, and then you write this open circle, which kind of looks like an O, but it's not an O, it's just an open circle. And you write f, open circle, g of x. And what this tells you, so this is a composition of functions f and g. So if f is composed with g of x, this tells you you're going to have the following. You're going to have f of g of x. Okay, let's break this down. Let's think about this. If we just had g of x, we already discussed that this is basically saying that g is a function and x is the input, right? Whatever you're plugging in for x, this becomes your input. And then because you're plugging in an input into a function, we know that you're going to get some number back, right? I'm going to call that number n, right? So you get some number back from this first, from this first function. However, we're composing two functions together. So we see that we have another function on the outside. So what's really going on? Well, what's going on is because you have this function on the outside, you're really now going to have a second operation. So you're going to have now you have a new input, which is whatever the number was from your original function. And now you get some other number, which I'm calling b. Okay, or we can call it m since we call the first one n. Okay, so the idea is I'm going to try to label as best as I can with colors. Your first function with the input, whatever the input is, in this case it's x, but it's going to be some different number or some combination of variables, right? So your first input into your first function gives you your first output. And then that output becomes your new input for your second function, for the outside function. And because you're putting in an input into a function, even though you're doing it a second time, you're going to get a new output. Okay, so when you compose two functions together, it's essentially like doing an input and an output twice. So one thing that you should be aware of is that order does matter. Okay, what do I mean by order matters? What I mean by that is f composed with g of x is not necessarily equal to g composed with f of x. And we'll see an example of that in just a second here. Okay, and once again, if you're not really following what f of g of x means, the example should help, break that down here in just a second. But we just saw that f composed with g of x really simplifies to be f being on the outside, g is your inside function of x, and we again see it's not equal, or not necessarily equal to your g being the outside function, f being the inside function, and x still being whatever your input is. Okay, so order does matter here. Okay, so let's work on an example together here. Let me scroll back up here. Let's let f of x equal negative 5x. And let's also let g of x equal x squared minus 3. So we have two different functions. What I first want to find, we want to find two things, and then one of your last thing that we're going to find here is your second classwork assignment, okay? So what I first want to find is, I want to find f composed with g at 0. So your first input is 0, okay? Then I also want to find g composed with f, also at 0. So we see here we're switching the order of the functions, but we're going to keep the input the same. The original input we're going to keep the same. We're going to see what happens. And then after we do these two, I'll let you guys go on your classwork assignment, okay? So let's do the first one, which is f composed with g at 0. So we have f composed with g at 0. And like we just talked about, this tells us order matters, right? So this tells us that f is your outside function. Whatever is on your left-hand side is your outside function, okay? So because f is the leftmost function, that means it's the outer function. So we have f and then g composed at 0. So what you're going to do here to try to figure this out is first you're going to be plugging in your input 0 into g. So into your function g. So you're plugging 0 into this piece right here first. Okay? So what this is going to tell us is we're going to have f composed with, well, we have x squared minus 3. So wherever there's an x, you're plugging in your input 0, right? So we have 0 squared minus 3. And 0 squared minus 3, we're going to keep that f on the outside. 0 squared is just 0 minus 3, so that we just have negative 3. And now notice we're left with a number again, right? We're left with a new input. So we're just going to take this new input. We started with 0, but 0 as an input spat us out negative 3 when we plugged it into g. And now that we have negative 3, we're going to plug this new input into f. So plugging negative 3 into this piece right here, which is the negative 5x. Okay, so what we're going to do here is, because we're just taking negative 3, plugging it in wherever there's an x, this is the same thing as negative 5 times negative 3. Negatives are going to cancel out. We're left with 15. So once again, just to quickly go over this, we started with f composed with g at 0. Our original input is 0, and because g is your inner function, that means you're plugging 0 in to your inner function first. That's going to give you some number. In this case, it gave us negative 3, and negative 3 serves as our new input to the outer function, in this case f. So we plug negative 3 wherever there's an x in f, and that's plugging negative 3 into here. So we get negative 5 times negative 3, which is 15. Okay, so 15 is the answer for the first composition. Let's do the second one. So the second one, going through it a little bit faster now. Again, our original input is 0, but the difference is now g is our outer function, f is our inner function, and again, 0 is your first input. So as a result, you're plugging 0 into negative 5x. So wherever there's an x, you're plugging a 0. So you have negative 5 times 0. And negative 5 times 0 is just 0, right? Any number times 0 is 0. So you have g of 0. Well, we actually already figured this one out before, right? G of 0, we did that right here. So we already know what we're going to get, but just to go through it one more time, g of 0, that means we're taking our new input 0. We started with 0 and we somehow ended with 0 again, but that's okay. So we're taking our new input 0 and plugging it in wherever there's a 0 in g of x, or I'm sorry, wherever there's an x in g of x. So we have 0 squared minus 3. So 0 squared minus 3, and we get negative 3. And now what I want to show you guys, what I want you guys to take away from this is notice how we got 15 here and we got negative 3 here. Order matters. Because you have g on the left-hand side, that means g is your outer function. Because you have f on the left-hand side, that means you have f as your outer function. Okay? Order very much matters here, so please do not get confused with this. Okay, so that was the first two. Now what I want to hand you guys off is I want you guys to try the classwork assignment. So the classwork assignment, and I'll write it over here, is I want you guys to try f composed with g at negative x. Okay, so give this a shot, see what you guys come up with, and we'll take it from there. Okay. Okay, so f composed with g at negative x. What does this mean? Well, once again, this tells you f is your outside function, right? Leftmost function is outside function. So f is your outside, g is your inside, and negative x is your input. So what this tells you is that wherever there was an x in g of x, so coming way back over here, we're going to be plugging in a negative x here instead. Okay, so we are now going to be plugging in f, and we have negative x squared minus 3. Well, lucky for us, negative x squared is really the same thing as x squared, right? So the negative just crosses out, and we don't have to do anything. So we just have f of x squared minus 3. Negative x times negative x, two negatives cancel. We're just left with a positive x squared, right? So we have f of x squared minus 3. We're almost done, but now we see we have a new input. And again, don't be confused. In the two previous examples we did, we only had a one particular number for plugging into our second function, right? We were plugging in negative 3 for our second, for our outer function, and we were plugging in 0 for our outer function. But it's okay to be plugging in more than just one thing, as long as this is your entire input. So our entire input here is x squared minus 3. What does this tell us? This tells us that wherever there's an x in f of x, so right here, we're going to be plugging in x squared minus 3. So plugging this in into f, we have negative 5, right? Negative 5 is the constant to the x that was part of our function f. So we have negative 5 times x squared minus 3. This piece used to be an x, but we plugged in the input x squared minus 3. Okay, so great, we plugged in our input. Now we just have to distribute and we're done, right? So distributing, we have negative 5x squared plus 15, and we're done. Okay, so that's all there is to it. Again, the entire idea here is just that you are taking a particular value, plugging it into your inner equation, it spits you out a new number or a new value, and you plug the new value into your outer equation. And that's it. And there could be an instance where you have more than two functions. So for example, if you have g composed with f composed with h of x, well, you just read this from left to right. So your outer function, your outermost function, is the left-handmost function, so g. And then your middle function, in this case, would be f. And then your inner function would be h. And your input originally is x. Okay, so reading it from left to right, if you have more than two, is still the proper procedure, with your left hand being your outer, and so on and so forth. And you just kind of, go down deeper and deeper into the hole, depending on how many functions you have. Okay. Okay. So last thing for 2.8 here is we have to determine, or we have to be able to determine the domain of a composite function. So just a couple minutes ago, we talked about the domain of a combined function. Now we have to talk about the domain of a composite function, okay? So the way that we do this is we have to still get the domain of a composite function to agree for all the functions involved, okay? But there's one key difference. We don't actually necessarily need to care about the domain of the outermost function, at least not by itself. And you'll see what I mean in a second. The procedure that we handle this is first we find the domain of whatever your inner function is, and then you get, so then you input the inner function into the outer function, and you find the next domain. And then you exclude any of the points where they disagree. I know that sounds like a lot of talking, so again, best way to go through this is with an example. So let's let f of x equal square root of x plus 1. And down here, we're going to have g of x equal 2 over x minus 3. And I want to find the domain of f composed with g of x. So again, remember that order matters here, right? So what is this really telling you? Well, f composed with g at x tells you that f is your outside function, right? G is your inner function, and x is, whatever your input is. So the procedure that we handle this is first we find the domain of the inner function. Okay, so that's always your first step when you're dealing with domain of a composite function. You find the domain of your innermost function. So in this case, our inner function is g of x. So we have to first find the domain of g of x. So to find the domain of g of x, you just think about your two constraints. Again, your first constraint is no negatives underneath an even-powered root, which we don't have that here, so you don't have to worry about for g of x. But your second constraint is your denominator can't be 0, so we set the denominator equal to 0 to find the point where that happens. So we say, great, x minus 3 is equal to 0, which means x is equal to 3, and this tells us when x is equal to 3, we get a 0 in the denominator, and it's undefined, right? We would have 3 minus 3 in the denominator, which is 0, and we have a problem. So as a result, our domain is all the numbers except for 3, so all the numbers to the left of 3, union with all the numbers to the right of 3. Okay, great. So we've now gotten the first step. We found the domain of the inner function. The next step that we have to do is we actually have to do the composition itself. So what I mean by that is we have to do this piece here. We have to take our function, g of x, and actually plug it in as an input to f of x. So what is this going to look like? Well, g of x is this piece right here, right? 2 over x minus 3. And this is going to be your entire input for wherever there is an x in the function f. So this whole thing circled is going to be plugged in and put in for that x that's in f of x. So let's write this out. We're going to have f composed with g at x. Well, this is equal to the square root of, because again, we're dealing with the square root. That's the first operation that we have. So we have the square root of, and it used to be x plus 1, but because we're passing in g of x as the input, now it is 2 over x minus 3. And is it a plus 1 or minus 1? It's a plus 1. Okay, so 2 over x minus 3 plus 1. The plus 1 piece, this is coming from here. And the 2 over x minus 3, well, that is once again being passed into this x. Okay, so we're taking one function and passing it in as an input for the other function. Okay, so what we have to do now is we have to find the domain of this piece now. So we found the domain of the inner function. Now we have to find the domain of the actual composite function, and then we eliminate the points where they disagree. So let's figure out what the domain of this is going to be. So notice, once again, that we can't have a situation where we have a negative underneath the radical, right? So we want to eliminate that from happening. So to eliminate that from happening, what we're going to do is we want to make sure that we set this entire piece to be greater than or equal to 0. So I'm going to have 2 over x minus 3 plus 1 to be greater than or equal to 0. Okay, well, to solve this, I see I have an inequality, and this is going back to, I believe, chapter 1.4, so feel free to refresh yourself. That's a couple lectures ago, but if you don't remember how to solve inequalities like this, we wanted to set one of the sides to be 0 because we want to use test points, right? We want to be able to figure out the interval using test points, so we want to see if it's positive or negative, and that's why we have one of the sides to be 0. So that works out for us, but what do we do with this plus 1? Well, we make it a common denominator. We make it into a fraction with a common denominator so we can combine the fractions. Well, we have an x minus 3 here, so I'm going to say 2 over x minus 3 plus x minus 3 over x minus 3. And again, this is nothing new, right? All we did is we turned 1 to be some number over itself, right? We agree that x minus 3 divided by x minus 3 should cancel out to be 1 if we really wanted it to. But we put it in this form so that way we have common denominators. And now that we have two fractions with common denominators, we just add or subtract the numerators. So now we have 2 plus x minus 3 over x minus 3. We can combine this and we get x minus 1 over x minus 3 is greater than or equal to 0. And we're at the point now where we can just use test points, right? And we know this because we have x is equal to 1. When you set the top and bottom equal to 0, we get x is equal to 1, and we get x is equal to 3. So on our number line, we know we're starting with 1, we know we're starting with 3, and we just have to test these 3 intervals. Again, if I'm going fast for you, if this is not making any sense, I very much encourage you to review the information that we did regarding inequalities or how to solve inequalities. This isn't going away. This is always, a relevant thing, especially for domain. Okay. So we have to pick 3 test points. I myself think that picking the easiest numbers is the easiest. So 0, a number between 1 and 3, that's not a fraction, 2, and then the next number after 3, 4. Okay, so I'm going to use those 3 points for test points. So what am I going to do here? I'm going to plug in my test points into this inequality and see if it makes the inequality true. Okay, so first I'm going to test 0. And testing 0, that means I'm going to have 0 minus, I don't know why I drew the parentheses, sorry. 0 minus 1 over 0 minus 3. Because remember, we had an x, right? Wherever there's an x, we're plugging in our test point. So 0 minus 1 over 0 minus 3. We know that this is going to be a negative over a negative, which gives us a positive number. Negative divided by negative cancels to be positive. And is a positive greater than or equal to 0? And in fact, that is true. So yes, that works. So this interval over here is going to be part of your solution. This one works out. And we put a plus there because we got, a positive result. Okay, so next up, we have to test 2. So testing 2, we have 2 minus 1 over 2 minus 3. We get a positive over a negative, which that gives us a negative number. Is a negative number greater than or equal to 0? The answer is no, right? So we get negative here. That is not going to be part of our solution. And also, we want to include these dots, right? Okay. The only dot that we may not want to include, actually, now that I'm thinking about it, sorry about that, I went on autopilot. We don't want to include 3 because when we include 3, notice that we get a 3 minus 3 situation, which is not in the domain, right? But we are definitely including 1. So, okay, last but not least, we have to test 4. So testing 4, we have 4 minus 1 over 4 minus 3. This is definitely positive over positive, which gives us a positive, which is absolutely greater than or equal to 0. So yes, this will check out, and this is another interval for us to use. So this one works out fine. Okay, so all we have left to do is, figure out the interval for this. So the interval is all the negative numbers all the way, starting from negative infinity, all the way up until we hit positive 1. We're including positive 1, so we have a bracket. We union this with the next intervals, which starts at 3 but not including 3, and this goes to positive infinity. Okay, so notice we have this domain here, and we also had the original domain way somewhere. Where'd it go? Sorry, I lost track of where I was. Here we go. Okay, and we have the original domain back here, which is negative infinity to 3 union with 3 to infinity. So we have to see where these agree, okay? So the fact is that we have to eliminate the points where they disagree, okay? So if this is all of the negative numbers, and it might help to write them next to each other. So we had negative infinity to 3 unioned with 3 to infinity, right? Okay, so we just have to compare these two domains. So once again, if you don't see it immediately, draw a number line. Draw a number line to make your life easier. See if this helps you out, right? So we have, for the following points on the graph, we know we're going to have a 1, we know we're going to have a 3, so a 3, and that should be about it, right? 1 and 3, and did I? Yeah, that's fine. Okay, sorry, thought I made a mistake. We're okay. Okay, so 1 we know that we're including for this thing right here. So I'm putting a closed circle there. 3 we know that we're always excluding for all of these domains, right? So I'm just going to put an open circle there. Okay, let's draw the circled one first, which I'm going to denote in red. So drawing the circled domain, this is all the negative numbers up until we hit positive 1. So I'm talking about all these guys right up there, and then from 3 to infinity. So all these guys over here. And now over here, we have, for the part in blue, we have all of the negative numbers and some positive numbers up until we hit 3. So we're actually including all of this and the open space over here up until we hit 3, but we don't include 3, and then all of these points afterwards. So what you're doing is you're just looking to see where the domains agree, and as it turns out, the domains agree basically for this domain that we have circled, because it's this interval right here, and we're including 1 in both cases, right? Since this, the blue line goes through 1, we know that 1 is definitely going to be a solution for our domain, and we're talking about this interval right here, right? So writing this one more time, it's from negative infinity to 1, including 1, but we don't include that blue piece because there's no red piece to accompany it, right? The domains don't agree there, so we disregard the middle section, and we union it with when it starts to agree again, which is starting from 3, not including 3, to positive infinity. And as it turns out, again, this is the same exact domain that we had circled, but it's not always going to be the case like that, okay? So this is your procedure. Oops, what happened? I don't know how I did that. Let's chunk that. Weird. But point is, this is your final domain. I know it sounds like a lot of work, but it's really not so bad. Let's go ahead and recap what we did here. So again, we are given the task of finding the domain of f composed with g of x. So to do that, what you do, your first step always, is you find the domain of your inner function. So in this case, g of x was our inner function. We find the domain of it, which we found to be this circled piece right here. And we found that by setting, of course, the denominator to equal 0 so we could find when we have that problem point, okay? So we found the domain of the inner function. Next thing that you want to do is you actually want to pass the inner function into the outer function. So we passed 2 over x minus 3, we passed g of x into the outer function f of x. Wherever there was an x in f of x, we passed in that 2 over x minus 3. And then we found the domain of this piece right here, right? We found the domain of this. So finding the domain of this, once again, all it involved was recognizing that you couldn't have a negative number. So because you couldn't have a negative number, you set it equal to be greater than or equal to 0. And we just did test points to figure out the interval of the domain there. And then the last piece that you're doing is you're comparing your two different intervals. So the one that has the blue arrow, the one that has the red arrow, you just see where the domains agree. And then you have your final domain, which is here, which I will denote as the domain of f composed with g of x. And that is all there is to it. Okay, so I know I've been going on for about 50 minutes here. There's one last topic that I want to get to. It's relatively short, and this will pretty much sum up everything that we have to do with functions, and we can move on from here, okay? So one last topic regarding functions, and this is going to be found in section 2.9. What we're going to be looking at is inverse functions. Okay, so what is an inverse function? Also, I should mention we're not doing the entire section of 2.9. We're just highlighting the important piece of it, which is inverse functions. So if you're following along in the textbook, again, it's not the entire section. Okay, so what is an inverse function? An inverse function, the way to think about it is that an inverse function is a function that undoes whatever the original function did. So whatever operations are going on to your variable in the original function, the inverse function is going to undo that. If you compose the inverse function with the original function, you should always get the original variable back. What do I mean by that? Okay, so firstly, you should see what the notation is for an inverse function. The notation is as follows. If you have f of x, sorry, I should zoom in more. Okay, if you have f of x, then the inverse function is notated as f with a -1 essentially as sort of an exponent. I know you're used to seeing exponents meaning, like squaring or cubing or something like that. For function notation, we use this -1 to denote that this is an inverse, okay? So this is just the notation you have to get used to. So what I mean by what an inverse function does is if you have your inverse function composed with your original function, you should always get your original variable back. This is in fact how you test to see if two functions are inverses of each other. If they are inverses of each other, when you compose them together, you will get your variable back. You should just get whatever your variable is, in this case, x. So if your variable was a y, you should just get y back, so on and so forth. Okay, and also the same is true if you compose it in the opposite order. This is the only time where order would not matter. So if you compose the original function with the inverse function, you should still get back your variable. Okay, so we should talk about how we actually find the inverse function. So let's try to figure this out together. So let's say we have let f of x equal x plus 2 over 3. And I want to find the inverse function f. So the inverse of f of x. Okay. And also, I'm not going to write it out, but secondary, I want to prove that this really is the inverse function. So after I find the inverse function, I want to show that or do a check that this really is in fact the inverse. So let's first start by finding the inverse function. The way that we do that is we start with the original. So original, once again, is f of x is equal to x plus 2 over 3. What you want to do is you want to substitute back, you want to go back into the equation notation. So if you guys remember, we substituted equations with functions. Well, now we're going to go backwards. And f of x, if you guys remember, was what we substituted for the dependent variable. So now we're just going to say, okay, well, y is equal to x plus 2 over 3. So we're substituting the function notation back to the equation. And now we have the equation notation where you have two different variables. Your next step is probably the most confusing, but once you get the hang of it, it's really not so bad. Your next step is you're going to switch the place of your dependent and your independent variables. So we see we have a y over here and we have an x over here. We're going to switch their positions, and then once we switch their positions, we're going to solve for y again. So let's switch their positions here, and we're going to have x over here now is equal to y plus 2 divided by 3. Notice all I did here was I just moved the x and the y to the opposite places. Okay, and our goal is, once again, we're solving for y. Okay, so solving for y, well, all I'm going to do is I see that I have addition and division going on here. So to undo the division, I multiply. So I'm going to multiply both sides by 3. We get 3x is equal to y plus 2. And now I am just going to isolate the y, which means I have 3x minus 2 is equal to y. And your last step Now that you've flipped the spots of your independent dependent variables, and now that you've solved for your dependent variable again, you can put this back into functional notation, but the functional notation is this is now going to be the inverse function. So this is now the inverse function of your original. Okay, so just to recap on how we solve this, we first started with the original function. We put it into the equation form where you have two variables now. You have your y in place of the f of x. You switch the spots of x and y, and you solve for y all over again. Once you've solved for y, you can then put in the function notation of the inverse. So now we have, instead of y, we have the inverse function of f of x. Okay? And now let's go ahead and actually show that this really is, in fact, the inverse function. And the way that we do that, once again, is we compose the functions together. And we see if we compose the functions together, if they really are inverses, we should expect to get just x back. So, and it doesn't matter which order you do it, I'm going to put the inverse order outside for no reason other than, that's just how I'm doing it here. You can do it the other way. So I'm going to have f of -1, or the inverse function on the outside of f of x. What does this tell us? Well, this tells us that we're going to have our input is f of x. So our input is our original function, right? So it's x plus 2 over 3. This is our input. So we come back down over here and we say, okay, x plus 2 divided by 3. And now, because this entire expression inside the parentheses is our new input, wherever there is an x in our inverse function, we're plugging in this new input. So our x is right here. So we're plugging in this entire piece into x. So what this gives us is 3 times x plus 2 divided by 3 minus 2. Okay, let's simplify. We have a multiple of 3 on the outside, and we're dividing by 3 on the inside, so we know that these can just cancel out. So those cancel out. We're left with x plus 2 minus 2. We see that these cancel out, and we're just left with x as we have expected. So we have now shown that this is, in fact, the inverse function, and if you did it the other way, you should still end up with just an x. Okay? So that is an inverse function. Again, the way that you think about an inverse function is it is undoing the steps that you are taking to your variable in your original. So if you think about what's happening to your original variable in your original function, we see that we're adding 2 to it, and then we're dividing that total by 3. In our inverse function, we are multiplying our variable by 3 and then subtracting 2 from it. And that's how we end up with this inverse function. Okay, so it's basically the opposite operations. Okay, so all I want you guys to do is to sum up this video, you can go ahead and try the third classwork assignment at this point. So that's going to be find the inverse of g of x is equal to x minus 3 over 2. So I want you to find the inverse function and then also prove that this is in fact the inverse function. So do the same steps that we just took where you show by composition that this really is the inverse function. Okay, so I'll give you a couple seconds to try to figure it out, or a couple minutes, however long you need, and then unpause the video when you are ready. All right, let's take a crack at this together. So once again, you start with your original, right? And I already have it written here. I'm not going to rewrite it, so we already have it here. Our game plan is you take your function notation and switch it back to an equation where you have 2 variables. So now you have y is equal to x minus 3 over 2. Okay, continuing along, what we have to do is we have to swap the positions of x and y. So now we have x is equal to y minus 3 over 2. And we solve for y. So solving for y, we multiply both sides by 2. We get 2x is equal to y minus 3. And solving for y, I add 3 to both sides. I get 2x plus 3 is equal to y. And as a result, we can now say 2x plus 3 is equal, is equal to the inverse of g. So the inverse function here. And So now that we found it, I just want to prove it that this actually is in fact the inverse function. And to prove it, all I'm going to do is compose my two functions together. In the last example, I had the inverse function on the outside. So for this one, I'm going to have the inverse function on the inside. So I'm going to have g composed with the inverse of g, which is g on the outside, and the inverse of g on the inside. And what does this tell us? Well, this tells us that the inverse function of g is going to be my input, right? So 2x plus 3 is my input. So we're going to have g with an input of 2x plus 3. And now with this new input, wherever there was an x in my original function, I'm plugging in 2x plus 3. So this 2x plus 3 is now my new input. And wherever there was an x in my original, that's where this 2x plus 3 is going. So we put, okay, we're going to have, what was it, x minus 3 divided by, oh, I'm sorry, instead of x minus 3 divided by 2, it is now 2x plus 3 minus 3 divided by 2. We can drop the parentheses here because, you know, there's no squaring or multiples that's going on. There's nothing that we have to distribute. So dropping the parentheses, we have 2x plus 3 minus 3 divided by 2. We see that the 3 and the negative 3 are going to cancel out. So those cancel. We're left with 2x divided by 2. And yeah, 2 divided by 2 crosses out, and we are simply left with x as expected. And we have now shown that this truly is the inverse of g. Okay, so that's all I have for you guys today. Hopefully this is not so bad. So, you know, if you guys, I imagine the worst part of this is the domain section and remembering how to handle domain of composition and also domain of combined functions. So make sure you have that down pat. I really recommend, you know, writing it down on an index card or something, just so, you know, you have it for yourself, because, you know, that's something that's very easily confused and I don't want you guys to confuse it. So try your hand at the homework. If, of course, if you have any questions, please let me know. Otherwise, enjoy the rest of your day or night whenever you're watching this, and I will see you guys next time in class. Have a good one.